Hello and welcome back to Dr. Logic Awkwardly Does Logic. We've just wrapped up our process for showing the completeness of S5, which I've emphasized many times is only for S5, and it doesn't tell us how to prove completeness of other logics. So I hope that by now you've been sitting here thinking, but what about all of these other logics? Are they complete? How do I prove this? I don't know, Dr. Logic. Help me. Well, have no fear. I am here to help you. We are next going to look at a general method for proving completeness. It's not going to be one that works in every single case, partly because there are some logics that are not complete, and so no method will work to prove that they are. Others, the thing is, modal logics are vast enough and disparate enough and expressive enough that it's not surprising that some of them are going to have really complicated sets of theorems or complicated semantics. And so there isn't going to be any one-size-fits-all method for proving completeness of all of them. However, the method that we're going to look at, it's the method of canonical models, is a method that works for a lot of really nice, well-behaved modal systems that have natural applications and that are kind of like the ones that you encounter most frequently in sort of philosophical applications. So that's why we're going to look at it, because it's a wonderfully general method and it has many applications. Also, along the way, we will get to see one of my favorite lemmas ever, so you've got that to look forward to. Of course, because this is a general method, this means there's going to be a lot of definitions and a lot of parts that we introduce, and it may not always be clear why or what they do or how this works until we bring them all together. So again, I'm going to ask for your patience because it will be worth it when we get to it. The stuff that we can do with the canonical models method is pretty awesome. So in this video, I just want to say a little bit about kind of like what it is that we are doing. So remember that when we are talking about completeness, it is completeness of a system of proof with respect to some semantics. And the idea is that the proof system is complete if everything that turns out to be necessarily true or a tautology or valid or whatever verbiage you want to use on the semantic side is something that is actually provable in the proof system. The proof system is complete in the sense that it doesn't miss out on any of the truths. This is why completeness is so important, because part of the reason of having a proof system is that it allows us to generate true things. And it'd be nice if we had some sort of reassurance that we could get everything that way. So that's why completeness matters. However, doing this in a direct fashion, as we did for S5, where we picked out something that was valid in the class of reflexive, transitive, and symmetric frames, and then we gave a procedure that generated a proof of it, this is not generally going to work with the systems that we're looking at. You might have something that you can demonstrate through semantic means has to be valid in this class of models, but this will in general tell you nothing about how to generate a proof for it. So what we're going to be doing in this new kind of procedure that we'll be looking at is proving completeness in a contrapositive fashion. So instead of saying, if this thing is valid in the class of models, then I can prove it in this particular proof system. What we're going to do is we're going to find things that don't have proofs and show that they aren't valid in the relevant class of systems. This will make things easier because then we don't have to kind of go through all of the possible proofs and say, okay, this one isn't a proof of the thing, this one isn't a proof. So we essentially get away from all of that mindless churning through proofs in hopes of finding the right one and just say, okay, I'm starting from the assumption that I have something that I cannot prove in my system, and then I will show that this thing isn't valid in the relevant class of models. It's not a semantic truth. That is the root of the canonical models method. The canonical model for a particular logic is going to be one where everything that is not provable, every non-theorem, somewhere in the canonical model, you can find a world where it is false. That is the basic idea of canonical models. In the future videos, we will make this much more explicit. There will be definitions. I will write all of this down. But right now, the idea to kind of put into your head and keep in your head for the remainder of what we're going to be doing in kind of this long arc is if something isn't provable, I can find a world in the canonical model that makes it false. And the canonical model is going to have a variety of interesting and important properties, which we will prove that it has. And therefore, the fact that it's false in the canonical model will be enough to tell us that it is not something that is semantically valid in our class of semantics. So that's the plan. Very abstract. Soon we're going to get very concrete, but very technical. And as I said, just bear with me through this because we're going to get to do a lot of really cool stuff. It's just all a lot of little pieces, and keeping it all in your head can be a bit difficult. So you might want to be prepared to watch some of these videos multiple times over until you really figure out what it is I'm trying to say. So that's what we have to look forward to. Until then, take care. Cheers.